I'm just making you a little bit self-conscious.
Well,
Okay.
like 3 people each, so it doesn't matter.
Let's have a look at this. Right. Learning intentions. Forces as a push-pull measured in newtons. So that's the unit. We've talked about that a little bit already. Newton's 3 laws of motion. Okay. The formula is force equals mass times acceleration, and weight is equal to mass times the force of gravity, which is 9.8. Okay. So you need to be familiar with these key terms. Force and net force, contact forces, Newton's 3 laws, what force diagrams are, etc. So let's have a look at this. Now, I'm not going to show you the awesome Slinky video at this stage. I'll show you that afterwards. But yes, I think I have already watched it, but we haven't asked about forces at that point. Now there's the first thing that we need to look at. Newton's 3 laws of motion. Okay? An object in motion tends to remain in motion unless an external force is applied to it, the law of inertia. Or an object that's not in motion will tend not to move unless a force, an unbalanced force, acts upon it. Okay? Force is equal to mass times acceleration. Now you should highlight all 3 of those because in terms of assessment you need to know, that's why they're all red, you need to know those 3 and effectively in order. So you need to know that the force is equal to mass times acceleration is the second one. For every action there's an equal and opposite reaction. Forces occur in pairs. So, for example, gravity is pulling me towards the centre of the Earth, but the reaction force of the floor is not pushing me, it's just resisting that to an equal amount. So I'm neither floating off into the air, nor am I sinking into the floor at all. I'm balanced in that sense. And that's a good example of the third one there. You can see here when the man jumps out of the helicopter, the force acting on him in free fall is a strong force arrow going down, and there's a little bit of wind resistance, so the arrow is quite small for wind slowing him down. But then when the parachute opens, so he's going to jump, there's a little bit of air resistance and he starts to get faster and faster, and then once he hits terminal velocity the arrows are the same, and then when he opens the parachute the arrow for wind resistance really goes up, but it still can't be bigger than the downwards arrow. Why is that? What would be the effect if the upwards pointing arrow in terms of the force of resistance was greater than the downwards pulling arrow? Is that
be slow?
Oh, he wouldn't be slowing, he'd be rising. If this arrow was larger, so there's a bit of an error there. If this arrow was larger, it would actually mean his motion would be upwards, and that could happen if there was wind blowing from below to rise him up. But in terms of a parachute, you want to have force of gravity, maybe 1,000 newtons, and the slowing power of the parachute at maybe 990 newtons, so you're coming down at a very slow rate, very gentle rate. Okay, now let's have a look at this. Now, how we measure forces, there's a few tools that we use. You're familiar with scales and springs in them and whatnot. And in terms of the bigger the force, the more the spring is squashed or stretched. All forces are measured in newtons. Now, 1 kilogram is about 10 newtons on the Newton scale. Where do you think we got 10 from in reference to 1 kilogram? It's about 10. It's actually 9.8 newtons. So it is in fact the mass 1 multiplied by the force of gravity, 9.8. So when we talk about, in this case, this is a measurement of weight, and we weigh, and the unit for weight is newtons, not kilograms. That's a measure of mass, and we'll talk about that in a little bit. But when I weigh myself on Earth, I'm 74 kilograms, but if I weigh myself on the moon, I'm maybe 12 kilograms, because the gravity has changed. The amount of mass I have hasn't changed, but the gravity has changed between those two. Now, let's go. Now here we start to get into force diagrams. Anything that changes motions get something going faster. And if velocity is increasing, then of course that is acceleration. So if you want to put a change in velocity there as a note, or slower is deceleration or negative acceleration. If you stop something, friction stops, slows things down and stops things. Change direction, twist or change the shape of something. Elastic objects bounce back into shape, that comes up almost never. In force diagrams, the length of the arrow shows the size of the force. Now, here's the girl looking just at that picture there, right, you can see the weight force is pulling down, mass times gravity. You have the reaction force of the ground pushing up. So that, and you should draw your arrows from the centre of the object. I should emphasise that. There's the reaction force, and these are exactly equal. There's a little bit of air resistance there, and then there's pedal force, or you could say thrust going in this direction. Now, in terms of motion, what is that girl doing? Is she accelerating? Is her velocity constant? She is accelerating. Does everyone see how we got there? This arrow is larger than the air resistance, so she is accelerating. If she was already riding, if she was doing 10 kilometres an hour and didn't want to accelerate anymore, at that point the arrow can be this big. The amount of thrust that she puts into the bike, if that's equal to resistance, but she's already moving, she will neither speed up nor will she slow down. There's a couple of things missing. There'll be friction here as well. So you get these tiny little arrows. A little bit of heat would be generated in the bearings of the bike. There'd be a bit of resistance there. And so, but they'd be small arrows there. But that is reasonable in terms of a diagram. Can I change? Okay. Now, here are some force diagrams, and you need to be familiar with these, and these are certainly on the test and the exam. Show all of the forces acting on an object, the force's direction, and its magnitude. Okay? The net force is the sum of all the forces. Okay? Now, if the net force equals 0, the object isn't moving. I'll tell you that one right now when we look at that in a second. Net force is capable of accelerating a mass if the wheels of the car push it forward with 10 newtons and drag is 7 newtons. The net force is 3 newtons forward. We should include a direction. You can see the little car over here. We have 10 newtons to the right. We have some wind resistance in the form of that parachute with a force of 7 newtons in terms of friction or wind resistance, air resistance. And so this car will either continue to move or will start to move forward with a force of 3 newtons. Now, what is the net force on each of the below boxes? Write your answer below each of those boxes. Net force on each of the below boxes. I'll give you a second. Doesn't take very long. Oh, there's a bit of note filling in yet. There's a little bit of Pythagoras theorem here as well, because a couple of years ago there was a question on a test that required you include Pythagoras. How are we going on the ones below? What is the net force in each case? Draw an arrow and include a number as your answer. Do the first one. Left is 20 newtons, right is 20 newtons. Is there any sideways motion? No. Up is 25 newtons, down is 25 newtons. Is there any motion either up or down? No. So what is the net force in the case of A? It is 0 newtons is the net force. There's no imbalance. Now the second one, 15 newtons left, 20 newtons right. Is there any imbalance? 5 newtons to the right. Up and down forces are identical, so in this case our net force is 5 newtons that way. Okay, so that object will move, or if it is moving, it will continue to move. In the third case, weight, 25 newtons down, reaction force, 25 newtons up. What is the net force in this case? It should be a very simple, hopefully you're thinking 0 newtons net force. And here we have another imbalanced one, 25 in weight force down, 25 in reaction force up, 20 newtons to the right. So that is in fact, the net force is 20 newtons to the right. The reason why I've put this here is, if you look here, if you have an upwards force and you have a force to the right, the actual resultant force will be a combination of those two, and the object will move in this direction. It will both go up and it will go right. Now, if we say the lift force is 3 newtons and the force to the right is 4 newtons, what would be the resultant force on that object? 5. And does everyone see how Harry got there? That's actually just Pythagoras theorem. That's a 3, 4, 5 triangle. And I've only ever seen that question happen once in 6 years, where we had an unbalanced force, that there were 2 unbalanced forces, so the object moved in on an angle, and you solve that using Pythagoras theorem. Okay, so a squared plus b squared is equal to c squared. 3 squared plus 4 squared is 5 squared, and the square root of 25 is 5. So that would be a highly unusual question. I don't think the students liked it. Now, this has got a bit of information on it, and there's a few things. What I've done in terms of creating this slide, we've talked about every force has an equal and opposite force. So here's our thrust force is maybe the thing that's moving something, moving the aeroplane, moving the car. A car uses internal combustion engine or electric motors to move the car forward. An aeroplane is using jet engines to move the aircraft forward. But moving it is thrust force versus friction force, which is the opposite force that resists movement forward. There's always friction of some kind in almost every situation. I've got a video at the end that shows a frictionless environment. And so you're trying to move something one way, and friction is not trying in an active sense, but is resisting that motion. Okay. Now, if your friction force is less than your thrust force, movement occurs. And remember that video clip I showed you where the man tries to run across the train line and slips and falls on the track and then gets out of the way? Not ringing any bells?
Yeah, I remember.
You should. We only did that last class. In that case, the friction force was less than his thrust force, but he actually, because the stones moved, he did not move forward. Now, support force or the reaction force, usually upwards. The ground is providing me with support force right now. The floor is. Buoyancy is also an upwards force, if you like. Floating. A lift force, flying an aeroplane. And tension force, springs, ropes, that actually happens at both ends. If I'm hanging from the monkey bars, I have force, effectively, I'm being pulled down in my arms, so I feel weight in my arms, but the monkey bar is in the opposite direction and is resisting my downward motion, so my arm is stretching a little bit, if you like, and the arrows in terms of my arm go from my elbow, one arrow up, one arrow down. The arrow should be the same. Now, versus weight force, always downwards, because gravity times mass is what weight is. Okay, so all of these are lifting forces, if you like, pushing up, and weight forces pulling down. An object in motion tends to remain in motion unless an external force applies to it. That's the law of inertia, and the diagram is an example of Newton's first law and the third law. What's the third law? Newton's third law. Go to the front of your booklet. Have a look there. What was what's the third law? Force is mass times acceleration is the second one. What's the third one?
For every action there's an equal.
Yeah, for every reaction there's an equal and an opposite reaction. So here's a push force, 40 newtons to the right. Here's Austin's push force, 40 newtons to the left. So that's net force 0 in that. Weight force down, support force up. So the overall force on that box is 0 newtons. Now has everyone finished filling in things? Those are some of the things we need to consider. And in terms of labelling, they are useful to have a bit of a think about those. Question 1. Now there's a diagram. There are some force arrows on the diagram. Is that balanced or unbalanced, the forces on that car?
Unbalanced.
It's an unbalanced because the thrust force is greater than the friction force. Okay? So, if the car is stationary when these forces are applied, or the car is stationary when these forces are applied, what will happen? So the car, when time is equal to 0, it is not moving, and then the force happens, and what does the car do?
Accelerates.
It is accelerating. It's going to move to the right. The thrust force is greater than the friction force, so the car will move and it will accelerate. So that'll be the first one. Okay. Now in the second case, if the car is already moving when these forces are applied, what happens? So the car is doing, we'll say, 20 kilometres an hour, and those forces are applied. Is it going to continue to do 20 or slow down when those forces are applied? Again, is the thrust force greater than the friction force? So will the car slow down? No. Will it speed up or will it stay the same? It's going to speed up. So it's going to go 20, 25, 30, 35. It's going to speed up because it's unbalanced. What would the diagram look like if the car was moving at a constant velocity? Draw the arrow for constant velocity on the car. So the car is doing 20. What would the thrust force need to look like if the car was doing 20 and was going to stay at 20? And this is why you would need a ruler in a test or an exam for using force diagrams, because you'd want to get that line pretty much exactly the same. It's about a pen long, so you'd need to go to about there. That was what the force diagram would look like for a car that's doing 20 and continues to do 20. What would the diagram look like if the car was slowing down? So we'll say that the car, we'll ignore that bit, we'll say that the car is doing a steady 20. How does the car slow down? There's two ways you can draw this. So, what are the two ways we can draw this? Draw them now for a car slowing down. That car is doing 20 kilometres an hour.
Yeah.
So, now get it to stop.
So we just make that longer, the arrow?
The friction force.
Yeah.
We'll say this friction force, I'm going to say it's from wind resistance, okay? So how would I get this car to slow down? How would I change the diagram to realistically slow the car down? Not many cars increase wind resistance to slow down. There's a couple. The tail will flip. So how do you stop cars?
You make that thing smaller or something.
So if the thrust force decreases, what does that mean? We are taking our foot off the gas, we're
Slowing it up.
well, you can decrease the thrust force. So decrease thrust force. I should draw an arrow. Decrease the thrust force. And what else can we do to slow a car down? Brake, which means increase friction here. That's the second thing you could be drawing. So if it's got four disc brakes, increase friction in the wheels, take our foot off the accelerator, and all of those things will serve to slow the car down. Okay, so this is just an introduction into force diagrams, and this is the way you need to be thinking in terms of drawing these forces using arrows. As a general rule, as I said, we draw the arrows to the centre of the object, but in this case I've drawn some small arrows there at the wheels to represent friction in the wheels is responsible for slowing that car down. Now, that wind resistance, as the car slows down, that wind resistance will also decrease. So if we drop thrust to 0, no thrust, and then, that's stop working, no thrust, but then we also increase friction at the wheels, then that car will come to a stop. Okay, forces can be push, pulling or twisting. Most forces touch the object, they are pushing or pulling around. Friction, air resistance, buoyancy can't be seen, but they do make contact. These are called contact forces. Now, interestingly enough, if you look at that little diagram for a life jacket there, each life jacket only provides about 10 kilos of buoyancy. 10 kilos of buoyancy is enough to keep you floating quite happily in the water, even though you might weigh, well, even though you might weigh 70, 80, 90, 100 kilos, because the heavier people tend to have more body fat, and which is buoyant in its own right. Now, if you're a bodybuilder and you weigh in at 250 pounds, I was going to say 120 kilos, Dwayne Johnson, you know, all muscle, no body fat, that jacket probably won't keep you floating in the water because you don't have much natural buoyancy. But there you go. All you need is 11 kilos. I don't think that anchor would stay. If that anchor is 30 pounds, is it going to float? How much natural buoyancy does an anchor have? None. It's solid iron, there's no air in there, and nothing in the anchor there are no molecules or atoms that are less dense than water, lighter than water. So unless that anchor is a very, very light anchor, that's going down. But that guy will be okay. There's an example of a parachute slowly bringing a person to the ground. The arrow going down is slightly greater than the wind resistance pulling back. So the person will slow down and gradually come to a fairly gentle landing. Gravity, magnetism and electricity act through fields. These forces don't touch the object, they're pushing and pulling around, and therefore they are called non-contact forces. I won't get you to do that exercise, but gravity, of course, is unusual. We've talked about that before. I mean, we don't have a great understanding of what gravity is. We can measure it really, really well. But it's a non-contact force proportional to mass. So the greater the mass of objects, it's also proportional to distance. So if you have, if you are very far from the Earth, even though the Earth is, you can still see the Earth, but effectively you won't feel much gravitational attraction towards it. So, and if the Earth was to double in mass, then the gravitational force generated by the Earth would also increase at that point. I don't think I had much for you to fill in on that page because we're not being tested on contact and non-contact. That's just magic. I'll show you that in a little bit. That you do need to know. That's an important one. Force is mass times acceleration. Okay, that's one of the formulas you'll need to know for the test and the exam. Now you'll notice that the unit ends up kilograms per meters per second squared, which is torturous, but that is what a Newton is. Okay, and you don't need to remember all of that. You just use Newton. That's what we measure forces in. And there's the little magic triangle. Again, I would highlight this because you don't get to take in a formula sheet into the test or the exam. You just simply have to remember how to manipulate these. Force is equal to mass times acceleration. Mass is equal to force over acceleration. Acceleration is equal to force over mass. Okay, so let's see. A rabbit with a mass of 2 kilograms accelerates at 2 meters per second. Find the net force on the rabbit. You should be able to do that in your head. Okay, what is the net force on a 2 kilogram rabbit with an accelerating at 2 2 meters per second. Hold up your hand, the number of fingers indicating the answer to that particular problem right now. How will you put the whole class? Don't do that. I don't understand less. Okay, so hands up. You should have the answers. Kate,
Yes.
answer to that particular problem.
That particular one.
Put the numbers into the equation. Force, mass is 2 kilograms, acceleration is 2, 2 2s are 4, and the unit is newtons. So that would be 4 newtons. Now, gravity. Non-contact force attracts objects with mass to each other. Normally a small force gets bigger the nearer you are to large or dense objects. So planets and stars, the force of gravity is proportional to mass. The force of gravity is proportional to mass and to a certain extent distance. We covered that as well. Now, the Earth's gravity keeps the Moon in orbit. Does the Moon also have gravity? And if so, can we see any of those effects on the Earth? Does the Moon have mass?
Yes.
Therefore, it has gravity. It's about a sixth of the Earth's gravity. The Moon goes around the Earth. Do we see any of the Moon's gravitational effects on Earth? Tides, which you would have done in Year 7. Does the Earth also go around the Moon? The Earth is wobbling on its axis. It's not going around in a big way, but the Earth, if that's the Earth there, the orbit of the Earth is a tiny little circle like this. So it is doing that, but you just can't detect it. We can't feel that. It can be detected with equipment, but we can't feel that. And the same thing's happening to the Sun. Even though the Earth is going around the Sun is doing a tiny little wobble because of the planets orbiting it as well. Okay. Now we've talked about force of gravity as measured in meters per second, and let's have a look. Any other questions about that particular slide? Okay. Now, finally, I think that's close to it. Oh, yep, there we go. Okay. Now, mass is the amount of matter or stuff in an object, and that doesn't change, and it's measured in kilograms. So if you're made up of, well, you're 37 trillion cells, and we'll say each cell has 100,000 atoms. I'm just pulling those numbers out of my hat. So we'll say that those numbers of atoms are constant. And it doesn't matter if you're standing here or standing on the Moon, you've got your 37 trillion cells with your 100,000 atoms per cell. Now, the mass of an object never changes, but astronauts are weightless in space. Their bodies haven't changed. Everything's still there, but the pulling force of gravity has decreased. So the weight force is a measure of mass multiplied by gravity. If gravity drops to 0, then you are weightless. If you stand on a scale, you will weigh nothing, but you still have mass. You'd still have your 70 or 60 or 50 kilos of mass, but you would weigh nothing. In science, we don't use weight in the same way that people on the street do. I weigh 74 kilos. No, I weigh 740 newtons. About. It's actually, how do I go about getting weight? Mass, 74 kilos, times 9.8. So it's less than 740 newtons. It's a little bit less. It's about 740 newtons is what I weigh. My mass is 74 kilograms. You'll need to get those units right. Why is it a force of about 10 newtons needed to lift a 1 kilo mass on Earth? Because you're lifting effectively against the force of gravity. Okay, so you need 9.8 newtons to move an object that weighs 1 kilo. Okay. Now, lastly, that hasn't changed. Oh, there you are. There's your weight on different planets. Okay, on Mercury, the gravity is only 0.38. So a 90 kilo person is now about 30 kilos. Venus is about the same. Earth's moon is a sixth, so a 90 kilo person is about 15 kilos. Okay. Mars is about a third, so that would be awesome. You'd feel quite good in term for a while, but your muscles are going to waste the longer you stay on that planet. Good. Thank you. Now, let's see. Venus, the happiest planet in the solar system. If you lived on Venus, why would every day be a great day? Sure, it's 400 degrees. It's unpleasant. That's tough. But why would every day? Yes.
Because a day lasts like 200 days on Earth.
It's a little bit more. But yeah, so that's part of it. Every day is your birthday on Venus. Yay. Literally every day is your birthday. Because it takes longer for Venus to go around the sun than it does. It takes longer for Venus to make one rotation on its axis, which is a day, than it does for the planet to go around the sun. So literally every day on Venus is your birthday. So you get cake constantly. Weight is measured in newtons. Done that. Neptune, Pluto is tiny. It's really a planetoid or a dwarf planet. Jupiter, 2.5 times. So on Jupiter, if you're a 70 kilo person on Earth, you're 175 kilos on Jupiter. And so it would be, and that's a pretty big strain on your heart and your skeletal system as well. So you would not be happy in that environment. I'm assuming you know Galileo's Leaning Tower of Pisa experiment, this idea that heavy objects fall faster than lighter ones in direct proportion to weight. That's the old idea. So the heavier the object, the faster it falls. But hopefully you know that, just apropos of nothing, so if I drop this pen, what's the rate of acceleration for a dropping object? 9.8? Yes. What about this heavier metal bulldog clip? If I drop it, what's its rate of acceleration? 9.8. Is there anything I can drop that doesn't have a rate of acceleration of 9.8? Okay, now, really watch this. This is my only magic trick for the day. In the first half second, what's the rate of acceleration of drop? 9.8. What about after 30 centimetres? What's the rate of acceleration? These are not hard questions. What if I drop it out that window and it falls 6 metres? What's its rate of acceleration? 9.8. Did any of you write down in your prac, it took a while for the weight to get to full acceleration? If you did, shame on you. It is always 9.8. That's the easiest question in the history of questions. 9.8. Okay, there's no, it takes a while to get up to full acceleration. It's always 9.8 from the very first nanosecond to the very last second of fall. It's 9.8. Velocity changes. When you tell me that it's not 9.8, what you're saying is when the weight falls, it doesn't have, the Earth's gravity isn't at full strength, and it takes a little while for gravity to get to full strength. That doesn't happen. The acceleration is due to the Earth's gravity. Yes, and we've already watched that film clip, bowling ball versus a feather, 9.8. That's why both objects in a vacuum fall at 9.8. Do I need to do these? Oh, that's a tricky question. Gravity gets smaller as we get further away from the planet. Gravity does depend on distance. So the force of attraction also depends on distance. It's an inverse square law. So if you double the distance, then the apple weighs a quarter. What is 2 squared? Not a trick question. 4. If you triple the distance, what is 3 squared? 9. It's 1/9. So when you move far from the Earth, not just a few meters. So when we talk about, when we have problems where people are on the Earth, and it doesn't matter if they're in a building or if they're on the ground, we'll say gravity is 9.8. But if you start to get onto satellites and get further and further from the Earth, then what happens is the weight decreases. And so, yes, if you were standing, well, let's have a look. Oh yeah, this key here. We'll say that is 6,000 kilometres from the centre of the Earth to the crust is 6,000 kilometres. It's a bit more. So if you go out to a total of 12,000 kilometres, so you've got to go quite a ways. 12,000 kilometres from the centre of the Earth, 6,000 from the surface, will get you, your weight will be 1/4. Okay. Let's have a look at that. Oh yeah. At this point here, yeah, your weight in newtons. So this is a 70 kilo person, 68 kilo person, and you can see progressively greater distances resulting in weight decreasing. I won't get you to do that because time is an issue. I might show you that. That's just kind of cool. But we're going to have to do, we'll have a go at those worksheets as well.